everyone. Good afternoon. A very long day, the Ocean Discovery Day. So thanks everybody for making this. It's a very special seminar today. We have Daniel
Gaebele.
Yeah, he's an R&D electrical engineer at Sandia National Lab, Water Power Technology Program. His research focused on the wave energy converter, control co-design, control co-optimization, socio-technical assessment of wave energy converters for blue economy applications, and seasonal wave energy converter deployment. Daniel did his bachelor and master in University of Stuttgart at Germany, and a PhD in electrical and computer engineering from Oregon State University, before he joined Sandia as the postdoc in 2024. So we are very happy to have you. It's yours.
Sweet, thank you. I'm gonna switch around between a couple of different presentations because all of the individual presentations have approval from my lab to be publicly shared, but if I would have put them into a new presentation, I would have needed to go through that process again. So bear with me. I'll be hopping around, and I hope the screen share works because that's kind of also running over my computer because I can't plug that into other systems. Yeah, thanks. I think Arzu captured everything about my history. I've been at Sandia National Laboratories since 2021. I'm not a postdoc anymore. We have a drastically changing group at the Water Power Technologies office right now because of all kinds of things that you can guess, but we're around about, I would say, 10 full-time technical staff members, about 4 or 5 postdocs, and always in a flux of interns, and a few of our interns are in this room, so good to see you again. And I think what is going to be a little bit interesting is what is a national laboratory, before I will go into the technical talk. Yes, Sandia is one of 10 or so Department of Energy national laboratories. And so we are federally funded, but we're managed by a private entity, in this case Honeywell. So as we speak, even though the government is shut down, we are not. We are federally funded, but we have there's a little bit more inertia in the systems. All our funds come from the federal government, but we have them, or some of them, in the bank already. So we can probably operate until around New Year without having to worry too much about the government shutdown. Still, fingers crossed that the shutdown doesn't last until the New Year, and we also wouldn't report to work anymore. Sandia is a huge laboratory, and a lot of the things that happen at Sandia are totally behind closed doors, and I'm also not aware of what they are. I live in this small little energy and homeland security space, and well, given the current situation, we might also be calling this a little bit different, and I will not be working in the renewable energy department anymore, but we're restructuring it. This is part of the process, happens more or less frequently to align with mission needs of the nation as a large. But within our renewable energy portfolio, we have folks looking at concentrated solar. There's a lot of wind energy research going on. Not so much hydropower, but quite a bit of water power as well. And my group does tidal energy, but a large part of us is just doing ocean wave energy conversion. And this is what I did in my PhD, and then started doing it at Sandia, and this is also what I came here to talk to you about. And I am gonna skip all of those, introduction slides, why marine energy could be quite complementary to other renewable energy sources. I will just dive straight into what we call wave energy converter control co-design. And I think some of you actually do the exact same work. And that's why I'm kind of especially excited to be here and maybe introduce some tools that we have been developing over the past years to make this rather complex topic. And complex here, I don't use that term lightly, I also mean it in the mathematical sense. How to make this more accessible. So this is a different presentation pieced together that Carlos, my coworker, was leading on introducing the wave energy converter optimization toolbox, and we call it WecOptTool, and more generally control co-design of WECs and the pseudospectral method that is the foundation of this open source WecOptTool that I'll show you actually later, and I'll show you some code. This kind of brief structure is like from a super high level, I'm trying to introduce you some control co-design and the pseudospectral method, run through WecOptTool code structure, because I usually think that's the hardest part about starting a new software. It's just like, where do I start? It's always new, and it's always kind of like, what do I do from here? And I hope to kind of reduce that barrier a little bit in that hands-on demo. And yeah, probably we'll do a Q&A after that too, and then we'll see how much time I have and see what else I want to show you or what you would be interested in. Control co-design. I always try to use control co-design specifically together, because co-design often terms in more social systems also could be interpreted as collaborative design, that you design something with a stakeholder. If I were to define what it means to me as control co-design, I would rather use the term concurrent design of algorithms and hardware. Speaking about hardware, well, you've all seen the hardware that's probably right out there in the lab, but on a fundamental level, it doesn't really matter what type of wave energy converter you're looking at. You can really describe the dynamics roughly with very, very simple linear models. The only important part that control co-design argues for is that you should consider all kinds of interacting dynamics concurrently, so at the same time. So there's kind of like, and a lot of methods from electrical engineering actually really offer themselves for this work here, because they do a lot with like very simplified linear circuits. The important part is just that we shouldn't differentiate between the electric circuit alone, like say the load and whatever happens on the control design, the controller, the actual software algorithm telling you how much to resist, but we should consider all the other components that really drive the dynamics of this overall oscillating system at the same time. So in a direct-driven WEC, those components that are driving could be how stiff is it? How much inertia has it? How large is the gear ratio between my, well, in this case, linear motion and rotary motion? So this is really the idea, control design, consider all things together. And I don't know, the delay is actually not that bad. Maybe, no, I'm not even gonna try to use the animations. I'll just run you through that slow and steady. And this is kind of like a super simplified visual of why you should be considering all those things, those interacting dynamics together. So now assume if you were to design machinery, so you move around in the geometry and PTO space. You make all your design decisions, you decide how large your gear ratio is. So basically, okay, you have defined, this is my hardware, this is what I'm going to use. Now I'm needing to decide how much should an electric machine oppose to motion of this buoy that is connected to some kind of mechanics. Well, then you kind of move around in that design space, the control design space. And you decide, okay, well, for this Boolean PTO, I found my optimal controller right here. But what you haven't looked at is this entire other space of PTO and control configurations that could be combined. And I think here it's worthwhile, because I think there's a lot of folks in the title industry or the field to make a different analogy. They kind of, actually I heard recently, but this system thinking applies to all kinds of fields, not just wave energy conversion at all. So for example, I listened to a talk where a researcher was talking about optimizing a turbine geometry. So their approach was they tested different number of blades. I think it was 3, 4, 5, and 6. Turned out, in terms of power, 4 they deemed to be the most effective based on a performance criteria. And then they, as a next step in the study, is well, now we'll take the 4 blades turbine and we find out what is the optimal solidity for that turbine. So they changed the geometry of the 4 blade turbine. But what they haven't looked at is like, well, sure, maybe this specific 4 blade turbine that they consider versus the 5 blade turbine performed better. But what would have been if you would have compared a lower solidity 5 blade turbine versus a different 4 blade turbine? So this kind of like system thinking applies in all kinds of fields. Like if there are variables that are interacting, you should consider them together. And really like truly independent variables are not that common. This kind of goes into the same, well, I guess this was more like a historic way of what folks have done in the ocean wave energy field. We're going from bottom to the top. This is basically what I love Fawn's book on ocean waves and oscillating systems. And a lot of what Fawn's considered and the derivation of optimal controllers is kind of this here. He considered a hydrodynamic body and then he designed an optimal controller to absorb the most power out of the ocean waves. But that would just mean it's kinetic energy now, nothing else. Fons did also consider in the same book, well, what if we do have losses in your drivetrain and so on? Would that optimal condition be different? So that's kind of like the next stage. Yes, still considered. But that still didn't consider anything but friction. So, and also designing the dynamics of the power takeoff so that they could potentially help the overall power flow from wave to wire. This is kind of like the entire motivation behind control co-design. Consider all the dynamic systems at the same time and in your optimization. But you can imagine that this becomes quite a challenging optimization task because it's such a large design space that you're looking at. This WecOptTool that we've developed, it employs a pseudospectral method to at least make the computation, the optimization, way more efficient. And can I get a show of hands who has used Simulink or other time marching dynamic solvers? 1, 2, 3, 4. Yeah, a few. Okay, so who's heard about, but like time marching solvers, is that, or time marching Euler method, is that everyone familiar with? Okay, yeah. I don't know if it does animate here, it probably doesn't. It's even very ruley on my end. Oh, not too bad. Okay, so on the left side is what you're used to. You start with an initial condition on the very left of that plot. You know your current state, and then with some form of integration method, you calculate your next step. Then you can do that and you march forward in time. The pseudospectral method, which is really, really useful for oscillating systems, which wave energy converters are, does it entirely differently. There's one major assumption that lies underneath it is that it's a periodic system that you're looking at. So the start and the end point will be the same. This is kind of a assumption that we need, and that works really well for WECs, at least in the operation that we're interested in, like the power operation. And so what this kind of way of solving does is pseudospectral. It uses time domain information, but looks at the frequency composition of those time domain signals to do all kinds of solving. So I always imagine it if we're then optimizing for an optimal controller, instead of an initial condition, you have an initial guess. Whatever your feedback controller is supposed to be, you start at 0. Well, but now what would it look like if there is a sinusoid with some kind of phase that you feed back? Do I go closer, like do I satisfy my dynamics, and do I optimize whatever I want to optimize? But because of this efficient way of going back and forth between time domain and frequency domain, we're looking actually at the entire time trajectory at once. So the curve over time, that's what I mean by a trajectory. We're always, at every iteration of the solver, we're solving for the entire time series at once. And this is implemented in the WecOptTool. And I think you've seen the logo of this tool, so I'm trying to explain it a little bit more why we chose it. So on this inside this nested loop here, this low level, you see the abbreviation of WecOptTool inside a feedback loop. The feedback loop here is just a visual representation of a control algorithm. This is what kind of always happens on the lower level inside the WecOptTool. You find an optimal control trajectory. And then on the nested loop, we kind of visualized, well, you could change something out here. For example, your WEC. And the WEC here is just represented with what we call the wavebot. That's just a little wave energy converter that lives in the desert in New Mexico. And so this control optimization on the lowest level here always happens by minimizing some kind of objective function. In a lot of cases, we would choose the average electrical power as objective function. You could think about other things, like if you were to integrate your WEC into a microgrid and the smoothness or the power quality is really important, you might not want to just optimize for average power. You might want to optimize it for some kind of different performance metric. Okay, and I think I'm going to I'm not going to skip this. I'm just going to go over it really quickly. And in the end, the only thing and only here is actually not a light task. What you have to do using WecOptTool is you do have to model whatever you want to model. It doesn't have to be a wave energy converter, but you have to be able to describe it in ordinary differential equations. And what we do is we usually write them in residual form. And in the slide before, you might have seen that the respective dynamics is kind of like formulated as a equality constraint in the optimization problem. And so what we do for WECs, which is really the simplest way of modeling a WEC, is using a second order differential equation and then just isolating, or not isolating, moving everything to the left-hand side and then describing the WEC dynamics in terms of its inertial properties and the forces that act on it to respective dynamics. One more really cool thing about WecOptTool and why we chose to implement it in Python. So if you haven't seen Python before, sorry, I'm going to show you some code. It always looks like a lot in the beginning. Python has a few libraries that allow for automatic differentiation. And automatic differentiation, like half of it is in the name, it kind of tells the computer how to differentiate a function more or less immediately. So if you look at the computational graph of the function x squared plus xy plus 2, the way you implement that, if you write that in code, x to the power of 2 plus xy, then if you use the right libraries, the computer knows its computational graph, and so it can also backpropagate what is the analytical derivative of this function. And the analytical derivative is really, really useful to have if you want to perform some sort of gradient-based optimization. So a gradient is like, you look at your objective function and you see how does my objective function change with respect to the independent variables that you're optimizing. And if you notice gradient basically more or less immediately because of automatic differentiation, it makes optimization really, really quick, and you don't have to blindly iterate and use finite differences to find the gradient and in which direction you're moving. I think I'm not going to go over this case study, but 2 photos of the wavebot that I mentioned, and the wavebot here you just see it's like as the little buoy, which itself is really dumb, but intentionally we put up the power takeoff system of the wavebot up here, which is, well, it's equally as large and very complex, a lot of sensors in there. So all of the things you see are based on numeric tools, but we've validated all of the theories that we kind of come out of those new optimization methods with real hardware. And I think now let's jump, there's a few more slides before jumping straight into the code. But I think, yeah, I do want to take you away that barrier of entry, so I'll show the code. The code structure, Python is an object-oriented programming language, so we do use objects quite a lot. And a lot of the functions that we are going to write, for example, for forces, they always need to have a WEC object. A WEC object has a lot of those methods that are just like, fundamental physics, some PTO configurations predetermined, just to make it easier. Then there is a dynamic state that always needs to go in a function, which would contain all the information needed to describe the trajectory in space of the WEC. Then a similar variable, xopt, is the optimization variable or the control stage, which you can kind of more freely decide how it's supposed to look like. As kind of the non plus ultra, the absolute best, you could say you have all the degrees of freedom as the WEC does. So you could optimize an entire trajectory that is not bound to anything, but you can also say, well, I want it to be a feedback structure which depends on my state of the WEC. So say if you want to do just damn the WEC's motion, you would say, what is the WEC's velocity? I multiply a constant by the WEC's velocity, and this could be then your optimization state, just like how much to multiply that gain. And finally, the last thing that always goes into the functions is a waves object, and the waves just contain spectral information over the waves that you want to consider in that case that you want to optimize over. So what we need to do to set up and run a WecOptTool case is define a WEC object, define the waves object, and define an objective function, and then call a method of the WEC object, the solve method, to optimize for it. And yeah, let's just look at that together, and I hope it's fast enough. Okay, so right here we're looking at just a Jupyter notebook. All of the Jupyter notebooks are on our GitHub page, and I'm sorry that I didn't have a link or a QR code online. If you Google WecOptTool GitHub, that's the first thing that will come up. There's all the software is available there, and all of those examples are available there to download and run. And I'm just gonna, is there any questions until here? Otherwise, I would just run through and WecOptTool and just to show you how it looks. Okay. It is Friday afternoon. For WecOptTool, we rely on a lot of other large libraries of functions. For example, the automatic differentiation library, Autograd, that we're using. Capitane, it's a boundary element solver for the hydrodynamics of the WEC. Some of you might be familiar with. And some are really just simple plotting libraries that are, if you're more familiar with MATLAB, would be right included. We are going to use a brute force optimization tool that comes from a different library in this example, which is really just it parameter sweeps basically over a space. And then the last line, that is the import of the WecOptTool as what. So all the functions that are hosted on GitHub will then be accessible through this little abbreviation WOC. Okay, so now let's go one by one through the necessary things we have to define. We're going to define the waves first, and we're going to use the waves module, which is a part of WecOptTool. And an X array is just a data format that you can use in Python. So one of the most important things actually for every optimization case that you're trying to set up with WecOptTool is the choice of a suitable frequency array. Similarly, as it's super important for Simulink models or time domain solvers, is depending on the dynamics you have in your problem to choose the right time steps and the finite time. Here we choose the right fundamental frequency and then the number of frequencies. And the frequencies that actually I want to show you, let's do, oh, I don't get the suggestions, so that might be embarrassing because live coding never works. Let's see. Nope, that's not it. There we go. So when we create this frequency array, which I don't need to pass this frequency array to other functions just yet. I just wanted to show you how it looks like. Is we start at the fundamental frequencies, and all of the following frequencies are integer multiples of the fundamental frequency. That is motivated by the fact that it makes the conversion from frequency domain to time domain really fast because we can just do matrix multiplication instead of Fourier transformations. And if we are looking at a regular wave input, which this example considers, we know if we excite one frequency, there won't be any spillage of energy to other frequencies that are not integer multiples of that frequency. So if we were to consider regular waves, this would be a poorly chosen frequency array, but I'm just looking at a regular wave example here. So that's why we're totally fine with just having a very, very rough frequency array here. You could ask, why are you not simulating one single frequency only? And that would be a great question. That is to capture nonlinearities. So even in a purely linear system, you wouldn't need to simulate more frequencies than a single frequency because all the energy stays there. This is where all the dynamics happen. In nonlinear systems, however, there could be, or the energy not just could, the energy will go to harmonics of the fundamental frequency. And we are considering some constraints in this example, thus introducing slight nonlinearities, but that's why we're going to use a frequency array and not just a single frequency. And I guess here's a good point. Oftentimes you hear, oh, frequency domain solvers, they don't allow for the same things that time domain solvers do. This is true, but WecOptTool is a time domain tool. It just uses frequencies very effectively to save computation time and enable some things that otherwise wouldn't be possible to formulate. Then when defining the wave, we just set a wave frequency of 0.3 hertz and an amplitude of 16 centimeters, and we call the waves module of WecOptTool and call the regular wave function to define a wave. And if we do that, we get this output for the wave, which is 10 frequencies long, and it has only energy at the very first frequency, which is the wave frequency is equivalent to the fundamental frequency, and it's surprisingly non-zero. I would believe, I think actually, I didn't specify a phase in a regular wave, so I believe if you don't specify a phase, it will be a random phase, and that's why there is a slight complex part of this complex wave amplitude already. Then, a WEC object. This is kind of like the...
Can I ask you a quick question about that?
Of course.
So you don't specify any of the amplitudes of the harmonics. In principle, when you run this system and you're computing at the other frequencies, are you looking to that self-self interaction of the primary wave generating other harmonics and then nonlinear interactions that evolve in the program?
Yeah, great question. No, it's all based on, like, the wave body interactions are all based on linear assumptions, and so there is no actual interaction between the body's motion and the ocean wave, in terms of that it would change the wave's frequency composition.
Can you specify nonlinear waves rather than linear waves by just specifying linked harmonics at certain amplitudes? They're fixed in phase to create a nonlinear wave.
Well, I don't know if I would call it a nonlinear wave. Something like irregular waves, yes, absolutely.
But so the phases would be independent then?
Yeah.
Right, thanks. Sorry, that's good.
Yes, the phases would totally be independent, and you can choose that however you want, more or less. Yeah, no, you totally can. Any other questions? Okay. For generating the boundary element coefficients, we're going to use Capitane, a different library, and so we have predefined in WecOptTool the geometry of the wavebot, which you can very easily change for all kinds of other similar conical shapes, really common. And we create a floating body, which is a Capitane object of the wavebot using its mesh. And we're going to just choose a single degree of freedom because that makes the analysis easier, and most of the power for the wavebot is contained in the Heave degree of freedom. And then we can solve the boundary element problem via Capitane. And that's taking longer than it should be, but I guess my computer was working hard. And so we get an X-ray data set as outputs that has added mass, radiation damping, a diffraction force, and a Froude Krylov force contained, and then the sum of diffraction and for Krylov is the excitation force. The inertia matrix is just the wavebot's rigid dry mass, and the hydrostatic stiffness coefficient, which all of those together will then make up our second order differential equations to describe the fluid body dynamics. And we're going to model the power takeoff systems of the wavebot in terms of a two-port system. So at the very beginning, I kind of showed you like a circuit representation of the wavebot. We're going to use some of those methods here to model the WEC, or the PTO of the WEC, means that even though it's a two-port system, they are linear functions of, the force that the PTO puts on the WEC would be a linear function of its velocity and a current on the load. And in an analog fashion, the load voltage would be a linear function of the WEC velocity and the load current. I'm not going to go into detail. We have a few papers if you want to see how to model different systems with impedances, and also, even though they're mechanical systems, you can describe them as an impedance, even though the unit is ohms and it is confusing. But in the end, it's just a 2x2 matrix that has 10 frequency components. So it's a frequency depending matrix that represents the dynamics. We're going to use this PTO impedance matrix to create a PTO object with predefined WecOptTool functions. And then we need to connect WEC and PTO, and we do that by defining an additional force, which we call the PTO force, and we're going to use the pre-written method, the PTO force on WEC. So the PTO's force as seen in the WEC frame, it considers trivial kinematics, and it was this function here. So on top of the hydrodynamic forces, we'll have another force, this additional force by the PTO. And so what WecOptTool will later do is how do I modulate my load current in order for this force to be beneficial for the overall energy conversion? Yeah?
And so for the PTO modeling, is it applicable for all the PTO systems, all the PTO types, electrical, hydraulic, or is it specific to?
Yeah, so this the question was if it's applicable to all PTO systems. I'll have to say no, it's not. This direct-driven wavebot PTO models really well linearly. The linear models are very good. If you would have some kind of hydraulic PTO with manifolds or some kind of rectification, linear models are really quickly at their limitations. So then you would need to write your own forces, which is in the end not that hard. It's just, it does require a fair bit more work from the user. And I'm happy to show some other PTOs that I model, but then it just requires, for example, a pendulum is now I write my gravitational force, or torque in this case. Short answer is the PTO impedance matrix is only good for linear PTOs that you can capture, the dynamics that you can capture well with linear models. If it's non-linear, you need to write the forces yourself. So the forces that then apply to the WEC hydrodynamic process, you would need to write yourself. And here, another part of the PTO would be constraints. And this is really one area where this type of optimization tool shines, that you can explicitly define your hardware constraints. So here's kind of more like a neat example. The wavebot is actually not that constrained, but if we were to constrain the max amount of linear force that the PTO is able to apply, we could do that with this function. Well, we could think, I guess I should say there is a limitation how much force that gear generator can apply. It is limited by the current you can run through the motor drive. It's just higher than 750 newtons. It's more like 3,000 newtons, but for the sake of this example, it's interesting to see that the force actually has to be clipped off. So here you see the first time that is not just in the background, actually, the function signature that I showed you earlier. So to this PTO constraint, you pass the WEC state, the optimization state in the waves object, and you call the PTO force on the WEC, and we say, well, that because we're taking the magnitude of it, the absolute value, we say that this max force of 750 Newton minus whatever the instantaneous force is, it needs to be larger equals 0. And larger equals 0 is just driven by SciPy, and it's not the intuitive, more common textbook way of formulating inequality constraints. Then it's just, the next few steps are just like, okay, we take this function, we put it in a dictionary, and then we'll put it into a list, because that's the form that the creation of a WEC object actually expect. So now to create a WEC object, we call another WecOptTool method. We add the BM data from Capitaine, the additional force from our PTO, and the constraint PTO, and then we have a WEC object. In this WEC object, it has, if you print it out, which we did here, it tells you a few things about the frequency components that it has, the degrees of freedom that it has, and so on. But by itself, it's not that helpful or meaningful yet. Last thing, objective function. I mentioned it a few times, very commonly for the sake of not having any better information. We just like, let's get the most power out of the ocean waves that we can. And very importantly, we should do that in terms of electrical power, because that's a transportable form of power. If we were just to absorb the most amount of ocean wave power, well, we would have converted into kinetic energy, and we can't really sell kinetic energy to anyone, really. So we are going to model electric power being the product of voltage and current, and that's already written in the PTO module, just with the function average power, and we're going to pass that to another variable that we call objective function, and then the objective function will be passed directly to the solve method. And now we're finally here. We are optimizing a trajectory for the wavebot for a single regular wave with a given PTO. And we did that in 8 iterations, which is really, really quick because it's a pretty simple, regular wave problem. And then we can start printing out a few quantities that come out. So the optimal average power that we optimize for, this 107.5 watts, is kind of the best you can get with the wavebot in that wave using that constraint. And now you could think of, well, what could I do different if you wanted more? Or we can start analyzing some components. Here, those two functions are just post-processing functions that are pre-written by WecOptTool to have one object with all the frequency domain components for WEC and PTO respectively, and an object with time domain quantities, because it's sometimes more intuitive to look at a curve in the time domain. This is how they look like, and now we can plot some of those functions. So now we were plotting the force that the PTO applies to the WEC, and we kind of see like one period of a force trajectory with a pretty cleanly clipped off sinusoid, which is just like 2 at the 750 newtons that we predefined as a constraint. In terms of electrical power, you've seen the phase shift here. So I believe the previous run I did, I don't know if you've seen the phase shift, but was just with a different random phase. We can see that the electric power most of the time is negative. In WecOptTool, I should have said that before when we looked at the average power. Negative power is power out. This is what we want. That's good. And in order to achieve optimal power out under the constraints, there were a few instances in time where the PTO provided electrical power to improve the hydrodynamic process. You can later analyze your controller, like, oh, would that be possible with a linear controller? Or what can I do to improve that? I think the last plot in here would be the Sankey average power flow diagram. So in the semi-transparent arrows, we're using a lot of the theory by Fons to say, based on this ocean wave and this hydrodynamic properties of the wave butt, how much power could have been transferred from wave to kinetic energy? That would have been drastically more than we actually converted in this simulated tank experiment. So all of these arrows, like in theory, we could have absorbed very close to 900 watts of ocean wave energy and converted it into kinetic energy. But somehow this tool decided that the optimal operation for electrical power happens exactly when you only absorb 136 watts of wave energy, and then you lose some more along the way to get to this 107 watts of average electrical power. And now I've been already talking for 50 minutes, and I apologize, but now that would be, the next question is to ask, how do we actually capture this? And this is what ties us back to wet control co-design. Now we would need to decide, well, different constraints, different components. Yeah, Martin?
Doesn't this limitation also occur because you specify the maximum power you want to have in the system? Maximum force?
Yes.
So that's your force, your allowable force is limiting the power.
Absolutely right. And that's something we can really quickly show if we were to increase it a bit. Well, by a bit, let's say double it. How much more would that do? Because that's a question you could really ask yourself, like, if my drive could handle double the current, well, how much power would that actually gain? Well, how much more power could I gain? So now we are at 170 watts. And you see now the force is clipped at 1500 Newton. And well, yeah, it is looking better. Yeah, still not good. And then you would need to, compare that drive, new drive, 2x my cost of the entire system? Probably not. But it almost no, not almost, but it's a 70% increase in power. And then this is how you would design or make decisions like that. Yeah.
Conversely, if you don't limit the power, it would optimize. If you don't limit the forces it can handle, it would could optimize for power, and then you would end up with insanely large forces.
That were to be true if you were to optimizing for absorbing power. Let's try it. I'm going to remove the constraint entirely. So instead of passing this constraint, I'm going to pass none. So that means the PTO can do anything. So now we're only at 197 watts. And yeah, you see a perfect sinusoid, that's the wave. The force profile, it's not limited by anything, but still we can't get all the power through the WEC. And if you have a few more minutes, I can totally show you why that is the case. Yes, I'm going to. This is, which is the best one? I think I have some, I want to go to. Do I have them small? So I bet the animation won't show well, but that is kind of like, it might be a slightly different wave. That's the wave, but the same case without any constraints. And if we were to look at this projection here, the color projection is the PTO force as a function of the WEC velocity, and the color shows the amount of loss. And losses are both associated with friction that we model in the PTO and winding resistance in the generator. So a very large force requires a very large torque, which requires a very large current, which drastically increases the dissipative losses due to heat and the generator windings, which is why the optimal operation for average electrical power actually doesn't require large forces. If you were to repeat that with the objective function being optimal mechanical power, then Martin, your intuition was absolutely right. You would require very large forces and very large motion. So yeah, there's that. So no, for average electrical power, if you have real systems, very likely the motions are not going to be very large. Yeah.
And what did you find mostly effective to just increase this power?
Yeah, great question. For a long time, not a long time, we've been thinking a lot, hey, we need more efficient generators. Like if we could decrease the winding resistance, then we could get forces for cheaper. And then basically have this reactive power almost for free going into the system. However, that's not that easy and also not the right approach. What we've learned since is instead of like applying reactive power from your active control algorithm, if you have energy storing components that could provide the same reactive power at the right time more efficiently than through your generator, you can really increase the power. And one of this component that we've played around with a lot is a negative magnetic spring. It is pretty hard to see here, but on the x-axis we have the stator position. Actually, I want the rotor position, that's the important one, at the stator retracted. So we're looking at that projection here. So for a positive, so I should explain, you can see all of the images of the magnetic spring in a couple of mass reports that we put out. But if you turn that magnetic spring in one direction, the magnet's attracted more and more and more the closer it gets to it. By definition, that's an unstable system that doesn't work forever, that only works until 135 degrees. If you were to exceed 135 degrees, it would just like switch over and snap into a stable equilibrium again. So, but yeah, the really like hard to wrap your head around the crazy part is that it instead of like pushing back, like most things do, like if spring stiffness, it actually, the closer you get, the more it pulls. And that's one element that can totally shift the phase of the entire operation of the WEC, which is really important for power flow into the WEC and then through. So basically, if you kind of separate the problem from a control-only problem to a control co-design problem, say, okay, if I can use other components, that works quite well. Yeah, if I can use other components and don't need to rely on my power absorbing element, the generator, to make an effective power flow, how does this look? And so in this animation, I'm kind of cranking up the drivetrain stiffness, so the magnetic spring stiffness in this case, and you can just see by doing that, always optimizing for the optimal controller for this WEC PTO configuration, you can actually capture most of the power that is in the ocean wave. But that, in the end, if you do reach that type of operation, you will see large oscillation amplitudes, large forces on your body, but they don't have to come from your power takeoff, or from the generator at least. The large forces then come from a different mechanical component. In this case, it was this magnetic spring. I know that's a lot to wrap your head around, but it's really cool because it works. I guess I can just share other things that is specific for a heaving buoy WEC. Like in theory, it's just the easiest to start and analyze, but a lot of other things, like for example, surging WECs allow for a lot more tuning of just like its natural oscillation period with with just like by, for example, changing the density distribution of your flow. So that's why a lot of folks that are using, well, actually, let me tell you about 3 developers that use heaving WECs. Core Power uses a huge negative spring, pneumatic in this case, to shift the frequency they want. And then there's Core Power and Aqua Harmonics in the US, but they just submerge their WECs so that they're under pre-tension and they don't have to act against so much restoring stiffness. Well, yeah, because they're submerged and always under tension. There's that. Yeah, Martin.
Third?
Oh, Core Power, Swedish one first, Calwave second, Aqua Harmonics third. Yeah. And then there's other wave energy companies that do heaving like Penthilasa who don't care about effective power flow. I think they know very well that they're not designing a WEC that would win the power flow competition, but it's out there and produces a little bit of power, and they're not concerned about capturing the most. And that's also a fine approach if they want to do something else out at sea. Yeah.
Is there a way to reduce your radiated losses there? Yes, we just developed that.
Yeah, that's a great question. You wouldn't want to reduce radiated losses because they are part of getting power from the wave into your hydrodynamic body.
Sidewalls.
Say again?
We have some sidewalls.
Sure. No, but it's really just like, like if your WEC oscillates in phase and oscillates more, there will be more radiated power. So I don't know if that would be the right objective, except you want to, well, it wouldn't be the right objective for power conversion, but you might have a different goal. And then it would be very interesting to formulate, some kind of objective function that gets you the most power while also having radiated power in mind. I've never done it, but yeah, if you're curious to. Maybe I'll just say a few more things about the tool. We know that it's really hard to get started, but the 3 developers I did mention first, they've all used it. Some supported by us, others independently. They have good things to say, and we would love to get students to use it too. And we know that it's a steep learning curve in the beginning, but if you can somehow incorporate it in your research, we can support you with our time. Oh, thank you so much. Yeah, we just got the link in the chat. Yeah, we can, weird times right now, we can't really support student work with funding, but we can support you with our time. Thank you.